Hello everybody, I am Hassan Dabaja from the Laboratoire d'Informatique et des Systèmes at Aix-Marseille University. I'm going to present to you my paper, which is a survey about vision-based structural health monitoring. The outline of our presentation is as follows. First, we will introduce vision-based structural health monitoring. Then, we will discuss several techniques: classical image processing, digital image correlation, 3D imaging and modeling, and deep learning. Finally, we will conclude our presentation. Let's start with the introduction. First, what is structural health monitoring? It is a set of techniques that's used to assess the condition of structures such as dams, bridges, and buildings. Vision-based structural health monitoring is a type of structural health monitoring where images are used. First, computer vision interprets the real world through images, and intelligent computer vision allows automatic identification of damages and changes on structural surfaces. Vision-based inspection involves raw image analysis, image enhancement, and autonomous image processing. Conventional inspection methods are often subjective, costly, and time-consuming. Vision-based structural health monitoring enables non-contact, low-cost, and autonomous inspection. Let's have some examples. First, what are some types of damages that could occur to a structure? For example, cracks. In the first image, we could see a crack in the fuselage of an aircraft. In the second example, we could see a crack in the hull of a ship. In the third example, we could see a spelling in a bridge. So, how could vision-based structural monitoring help in assessing these damages? So in the first example, we could see the inspection of bridges using drones. The drone could go to specific areas in the bridge, collect images. These images are analyzed using vision-based structural health monitoring techniques, leading to identifying the damages. There are two levels for vision-based structural health monitoring. On the local level, techniques such as image classification, detection, and image segmentation are used in visual images or infrared images to assess conditions such as cracks, spelling, corrosion, delamination, and void on the surface of a structure. Cracks are linear fractures or separations in the material. Spelling are loss of surface concrete, often exposing the reinforced steel bars. Corrosion is chemical or electrochemical reaction in the steel reinforcement, usually forming rust. Delamination is separation of material layers, usually parallel to the surface. And void is empty spaces or air pockets within the material. However, on the global level, the overall structural behavior is monitored, providing a comprehensive assessment of structural health. For example, classical techniques such as optical flow or visual tracking are used to assess structural responses such as displacement, vibration, model parameters, cable force, and curvature. Techniques such as object detection are used to assess external loads. An important goal in vision-based structural health monitoring is fatigue crack detection. And crack detection methods are usually divided into two types. First, patch-based, which is identifying cracks within small image regions, which are called patches. This is done using pattern recognition, template matching, or machine learning, or other techniques. And the other type is pixel-based, which processes the entire image directly, segmenting cracks from the background and the pixel level. In this presentation, we will discuss four types of vision-based techniques that are classical image processing, digital image correlation-based, method based on 3D modeling, and deep learning methods. Classical image processing include feature extraction and image enhancement for damage detection. Digital image correlation-based methods, they allow for accurate measurements through monitoring surface displacement, which can provide crucial information about strain and deformation. Methods based on 3D modeling, they provide a detailed view of parts of the structure, which enhances the accuracy of damage detection. And the deep learning methods, they are based on neural networks, which are applied in real-time automatic detection, and also in efficient classification of structural defects. And now we will move to classical image processing techniques. Classical image processing extracts critical information from images. Binarization, image correlation, and fractal analysis contribute to damage detection. Edge detection, thresholding, segmentation, and filtering allow comprehension of structural condition, and image classification, optical flow, and visual tracking enhance the ability to monitor structural integrity over time. Now we will talk about thresholding. Thresholding is a basic image processing method. It divides an image into foreground and background areas by analyzing pixel intensity values, such as damaged and undamaged areas. This method is fast, simple, and ideal for resource-constrained applications, but it relies heavily on image contrast. Examples: for example, adaptive thresholding. It improves results by adjusting the threshold locally to address these challenges. Region-based segmentation. It groups pixels into regions using similarity criteria like intensity or color. K-mean clustering. It segments images by grouping pixels into K clusters based on intensity or color using distance to centroids. Edge-based segmentation. It detects region boundaries by identifying intensity changes using operators like Sobel, Peruit, and Kani. Lastly, the Otsu method. It automatically finds the optimal threshold to separate image into foreground. And then edge detection. It can be used in monitoring structural displacement and in detecting structural damage. Another type of classical image processing techniques is filtering. There are different types of filtering, such as spatial filtering and temporal filtering. First, spatial filtering. It improves image quality by reducing noise and enhancing important features. There are different types of spatial filters, such as averaging, median, adaptive, high pass, and morphological. Averaging filter, it blurs images by replacing pixel values with average values of neighboring pixels. Median filters, they work well for impulsive noise and retain sharper edges compared to averaging filters. However, larger kernels still render the image blurry. Adaptive filters, they respond to local image content and hence can offer improved overall noise reduction while preserving edges. High-pass filters, they include Laplacian and unsharp masking that highlight subtle damage features like fine cracks. Morphological filters, they use operators like erosion and dilation, and they are effective for noise removal and gap filtering. Now we will move to temporal filtering, which include Kalman filtering, which tackles feature points in videos by leveraging temporal correlations. Temporal averaging, it reduces video noise. Frame differencing, it highlights structural changes, but it is noise sensitive. And finally, optical flow algorithms. They estimate pixel motion for displacement measurement, but they are computationally demanding and noise sensitive. Now we will discuss digital image correlation. So what is digital image correlation? It is used in structural health monitoring to assess the integrity and longevity of structures. It captures sequential images of a structure under load using high-resolution digital cameras. It uses correlation-based matching to calculate deformation by monitoring pixel gray levels. It generates 2D and 3D strain charts and vector fields. It has several advantages. First, it analyzes displacement, strain, crack propagation, material defections, and structural damage. It is robust, accurate, and has high spatial resolution, and no spatial illumination and minimal surface preparation is required. There are two types of digital image correlation, which are 2D and 3D. 2D digital image correlation requires a single camera. It measures planar deformations only. It has a limitation, which is optical distortion and camera distance sensitivity, and the application scope is limited to flat surfaces. However, 3D digital image correlation requires two synchronized cameras. The measurement type is 3D deformation, which are curved and planar surfaces. It minimizes distortion and distance sensitivity, and the application scope is border, including curved and complex surfaces. Another type of digital image correlation is digital volume correlation, which extends to the digital image correlation by measuring internal deformations in opaque material using 3D volumetric images. Advancements in digital image correlation include high-speed cameras, drones, optimized speckle patterns, improved correlation algorithms, and better camera calibration. Let's move to 3D imaging and modeling. 3D modeling techniques improve the quality of detection and analysis and visualization of structural damage. Advantages: comprehensive visualization and evaluation of structural components, detection and analysis of stress, strain, and damage patterns, simulation of structural responses under various loading conditions, and identification of critical failure-prone areas. Applications: they include identified damaged areas in bridges, detecting pavement cracks, and fatigue crack detection in steel bridges. Advancements include 3D reconstruction with UAV imagery, modeling with the aid of deep learning, and integration of data from LiDAR. Now we will discuss deep learning techniques. Deep learning models are classified into supervised learning models, unsupervised learning models, semi-supervised learning models, and self-supervised learning models. Supervised learning models are widely used for crack classification. Unsupervised learning models, such as cyclic GANs, are used in crack segmentation. Semi-supervised learning models address concerns about data quantity and quality, incorporating limited labeled data. Self-supervised learning models emphasize the effective use of limited labeled data. Convolutional neural networks, they are powerful tools for detecting surface or structural cracks in images due to their autonomous feature learning capabilities, especially when enhanced by contour analysis, edge detection, and color thresholding techniques. Some examples are VGG, ResNet, and DenseNet. They are recommended for crack classification. Recurrent neural networks RNNs are great in handling sequential data from sensors. Recurrent CNNs (RCNNs) and long short-term memory networks (LSTMs) can excel for tasks requiring the combination of spatial and temporal information. Faster RCNN, RetinaNet, YOLO, and SSD can be used for crack object detection. Faster RCNN has superior accuracy in locating and categorizing cracks. Masked RCNN, UNet, and pixel-to-pixel are used for crack segmentation. Now we will discuss transfer learning. Transfer learning is an important tool in structural health monitoring for training neural networks in image classification tasks. Principle of transfer learning is as follows. It involves using a neural network pre-trained on a larger dataset and fine-tuning it for a new analogous classification task with a smaller dataset. An example is as follows. In CNN, convolutional layers may be freezed, while fully connected layers could be fine-tuned. Advantages of transfer learning include reducing training time, lowering computational cost, and less extensive data requirements. Retrained neural networks utilized in structural health monitoring include AlexNet, VGG16, ResNet, GoogleNet, and ZFNet. CrackNet and the CrackNet-V are CNNs designed explicitly for crack detection on 3D asphalt surfaces. They showed robustness, performance speed, and high precision. Fully convolutional networks are used for image segmentation, surface defect segmentation, and crack inspection. UNet, SegNet, Mask RCNN, PSPNet are also used for image segmentation. Now we will move to the conclusion. Vision-based structural health monitoring has recently progressed remarkably. Traditional methods, such as edge detection and thresholding, have significantly contributed to the damage detection field. Digital image correlation allows accurate measurement of structural displacements. 3D modeling techniques improve the quality of detection, analysis, and visualization of structural damage. Deep learning combined with transfer learning is powerful in crack detection, segmentation, and classification. Future work will focus on real-world performance comparisons and analyzing their impact on predictive maintenance outcomes. Thank you.